hole-sized rods streak down from outer space and obliterate targets on Earth.
It would be the ultimate bunker buster.
Powerful lasers instantly blast enemies in any direction.
You'll get zapped at the same time that you see the zapper initiate the zapping.
Missiles traveling near the speed of light deliver massive blasts without the aid of explosives.
It starts to become possible to hit things with the energy of an atomic bomb without actually having to use any sort of radiation.
And space pilots battle to the death in a very different kind of dogfight. These aren't just sci-fi fantasies. They are the future of space wars in the universe. It's 100 years in the future, and the final frontier has turned into the ultimate battleground. A rogue colony on the moon has already attacked neighboring colonies. A spacecraft from Earth has moved into position after negotiations have broken down.
As we travel out into the solar system and maybe even the stars, there are going to be people who disagree with other people, and the potential for warfare is just as great there as it has been any time through human history.
Before the rogue colony takes any more innocent lives, the spacecraft releases a weapon of unimaginable power, an antimatter bomb. Antimatter is the same as normal matter, except with the opposite atomic charges. Instead of negative electrons and positive protons, antimatter has positive electrons and negative protons. When matter and antimatter touch, they instantly annihilate each other, releasing a huge amount of energy.
When you have antimatter colliding with matter, all of the mass gets converted into energy. 100% efficiency. That's a lot of bang for the buck. Even nuclear weapons are only about 1% efficient. Chemical weapons are a tiny fraction of a percent in terms of their efficiency.
A warhead of normal matter would simply explode when it came in contact with the antimatter inside. The antimatter bomb streaking toward the rogue colony is a mass of antimatter surrounded by an electromagnetic field. Just before impact, the field is turned off.
You don't even need a fuse, you just need that antimatter to reach the desired destination and hit it. And it will then convert all of its energy and the energy of the object that it hit into this explosive energy, producing a tremendous explosion.
Other spacecraft in orbit around Earth target smaller remote outposts loyal to the rogue colony with powerful laser weapons.
An advantage of a laser weapon is that the laser beam travels at the speed of light. So you could have these light beams going across very large distances in a very small amount of time, zapping the enemy before the enemy realizes what's going on.
Light races across the universe at 186,000 miles per second. So the futuristic laser weapons fired from orbit near Earth take just over a second to blast holes in their targets on the moon, about 240,000 miles away. But just because we're 100 years in the future doesn't mean simple projectiles have disappeared from the battlefield. They inflict damage by slamming into the enemy, using what's known as kinetic energy, the energy of motion, to destroy a target.
If we accelerated some kind of mass up to sizable fractions of the speed of light, we wouldn't even need a warhead. Just the kinetic energy of the motion of that object itself would have an incredible destructive power.
Like an asteroid impacting a planet, the more an object weighs, its mass, and the faster it's going, its velocity, the more kinetic energy it has. But velocity has an advantage over mass in the kinetic energy equation, since mass is multiplied by the square of the velocity.
So something traveling twice as fast has 4 times the kinetic energy of something of equal mass. So you get something up to very high velocities, it has a lot of kinetic energy.
The different amounts of kinetic energy are easy to see when hitting a target with the same type of projectile traveling at 2 different speeds.
This firearms expert is going to fire 2 identical lead balls. The first from this smoothbore pistol. The second from this smoothbore musket. Now with its longer barrel and larger powder charge, it's going to fire that ball much faster. Let's see.
First, the pistol sends the ball downrange at a relatively slow speed. Now the musket fires the same sized lead ball at a higher speed.
On the back of the target, you can see the damage caused by the lead ball fired from the pistol. But now look at what happened with the lead ball from the musket. Much higher kinetic energy, much greater damage.
And out in the vacuum of space, there's no atmosphere to slow things down. So another ship in Earth orbit launches a telephone pole-sized projectile made of dense metal at the rogue colonists' underground headquarters. It's known as a rod from God. After a brief rocket boost, the acceleration of gravity gets the non-explosive rod moving at more than 10,000 miles an hour by the time of impact.
As we're able to get heavier and heavier objects moving at faster and faster velocities, it starts to become possible to hit things with the energy of an atomic bomb without actually having to use any sort of radiation.
The heavy metal rod penetrates layers of moon rock to destroy the underground command center. Without explosives, kinetic energy alone has devastated the area. Like an asteroid, creating a huge crater. But no matter how advanced space weapons become, one of the basic principles of warfare and technology will probably still apply.
I think it's an inevitable fact of human nature and human history that the invention of one weapon and its use triggers a countermeasure or a way to try to defeat it or build a better one. So you're going to see that in space weaponry no matter how far in the future you go.
A fantastic countermeasure against a directed energy weapon like, say, a laser would be a cloaking device like we see in many science fiction shows like Star Trek. If we can render a ship invisible, then electromagnetic energy just passes right through it.
But the technology to make entire spaceships invisible, or the power needed to create lasers strong enough to blast big targets from vast distances, are well beyond our current capabilities. And right now, there aren't any offensive weapons stationed in space. But war could still come to space within the next decade or so.
The future of space warfare may look a little different. At first, I think it's going to be satellites and anti-satellite systems, missiles and satellites, not manned systems at all.
And why would satellites, and the weapons that can destroy them, likely be the focus of the first space war? Because satellites are already essential to fighting wars on Earth.
America, in particular, is extremely dependent on space. Our military cannot operate the way it does today without satellites. We use them for communications, navigation, intelligence gathering of all kinds, whether it's photo intelligence, whether it's signal intelligence. A lot of it is done by satellites. Even ground maneuvers require very accurate positioning, GPS signal.
Since 2007, China and the United States have proven they're capable of destroying satellites in low Earth orbit with missiles. They've each taken out one of their own satellites. It's no easy feat since the satellites are streaking across the sky a few hundred miles above Earth at about 17,000 miles an hour. Without fast computers, people wouldn't stand a chance.
Hitting a satellite in space with a missile is as difficult as hitting someone else's tennis serve with yours. Getting the timing, getting the speed right, it's virtually impossible. But for a modern missile with advanced technology, it's not that difficult. These missiles have sensors that allow them to determine their own location and the target location and changes and make split-second adjustments and hit them. Imagine if you had a smart tennis ball using the same kind of sensor technology, adjusting its location hundreds of times a second to make sure it hit the target.
And once a missile intercepts a satellite, a big explosion isn't needed. In fact, many anti-satellite missiles are designed to simply ram their target without any explosives at all.
Space-based materials are designed to be fairly light. It's very expensive to lift things into orbit. It takes about 100 pounds of fuel to lift 1 pound into orbit, so you want to make things as light as possible, which makes them also usually comparatively easy to knock out.
And back on Earth, the effects of an all-out space war in the next decade would be severe. If countries begin blasting each other's satellites out of the sky, the problems would quickly spread beyond making it difficult for the military to wage war.
Today's global society is definitely dependent on space. If we were to start losing satellites, not just military satellites, but commercial and civil satellites, what would happen to daily life? Suddenly, ATM machines don't work. Many cell phones don't work. Pay at the pump no longer works. Financial transactions all over the world that use the GPS timing signal all of a sudden are disrupted. So the whole world slows down.
And if a space war escalated totally out of control, missiles might carry nuclear warheads into space to make sure important targets were knocked out with a big blast. But you won't believe how different a nuclear blast in space looks, and how destructive it can still be back on Earth. There's one weapon in today's arsenals that might still be used to annihilate targets in massive space battles of the future: atomic bombs. But anyone used to seeing atomic explosions on Earth would have a hard time recognizing these blasts in space.
One of the creepy things about exploding a nuclear weapon in space is it doesn't look like anything you'd expect. Here on the planet Earth, we see this iconic mushroom cloud. But in space, with no atmosphere, there's no cloud. Instead, you have an expanding bubble of radiation, a single flash of light, like a star, very small, going supernova.
In the first few nanoseconds, high-energy gamma rays explode in all directions, along with a flash of light, followed by an expanding cloud of radiation. The shockwave that rips buildings apart on Earth is gone, since there's no atmosphere in space. But the sphere of radiation expands faster and farther than on Earth.
You can just think of almost like bullets, but they're radiation particles going out, and they will travel a long ways. Gamma rays, neutrons. They will penetrate satellites. Some go blasting right through. Others hit electronics and cause a lot of damage.
With an average-sized nuclear bomb, any satellites within a 50-mile radius will be destroyed. But an atomic blast in space wouldn't just destroy equipment.
Astronauts flying through the debris from an exploded nuclear weapon in space would be subject to extreme levels of radiation. In particular, there are gamma rays coming from radioactive decay of radioactive nuclei, and they can interact with skin and cause cancer. Also, there are energetic electrons and other particles coming from these radioactive nuclei, and all of these things are damaging to living tissue.
Without any wind or other atmospheric effects, that expanding sphere of radiation would stay at dangerous levels for months. Today's missiles can carry nuclear warheads into space, and due to the way atomic bombs interact with Earth's upper atmosphere, one country might decide to target another with a blast in space because it actually causes a lot of damage all the way down on Earth.
When a nuclear weapon goes off above most of the Earth's atmosphere, it releases a bunch of gamma rays, very high energy electromagnetic radiation, that ionize the gas in the atmosphere. That is, they kick the electrons off of the atoms and molecules. Those electrons are kicked largely in a downward direction, and they're moving at a substantial fraction of the speed of light. Now that creates an incredible electric current, and that can set up big voltage differences and big surges of current in electrical equipment here on Earth.
So if America were the target, there'd be a sudden spike of current known as an electromagnetic pulse, or EMP, coming down like a massive invisible ball of lightning. It destroys electronics and anything else carrying an electric current in an instant. Atomic blasts on Earth also create EMPs, but with more limited ranges. By exploding above the atmosphere, a single atomic blast could devastate the country.
It's been estimated that if you lit off a 1 megaton nuclear weapon 100 kilometers over Kansas, you would render most, if not all, the electronics in the United States inoperative.
The damage on Earth from atomic explosions in space isn't just theory. Starting in the late 1950s, during the height of the Cold War, both the United States and the former Soviet Union became the only nations to use space as a nuclear testing ground. One of the last tests, in 1962 above the Pacific Ocean, created an EMP that knocked out electronics all the way from New Zealand to Hawaii.
So you can affect a large area with these currents, these sharp currents, not just the immediate area right below the bomb.
Because of the widespread damage in space and on Earth, both countries stopped these blasts after less than 24 tests. To avoid hitting friendly satellites or spacecraft with big, imprecise nuclear blasts, conventional firearms could be used in space. But if you were in charge of security outside of a space station, would a normal handgun even fire without atmospheric oxygen in a microgravity environment?
Gunpowder has its own oxidizer built into it, so it would fire. If you managed to get the firing pin to hit the end of the bullet, it would go off. Now, would it eject the slide and the next bullet go into the round, and would that work? That's a good question. I'm not real positive that it would fire more than a few times before it seized up and quit working.
A big part of the problem is that the metal moving parts inside guns need lubricants to work smoothly. But the harsh extremes of space would probably cause the lubricants to fail.
If a handgun got in the sunlight, for example, it would get really, really hot, and the parts would seize together probably. If it were not in the sunlight, it would get really, really cold, and the parts would seize together probably. And lubricants just have a hard time of working in the vacuum of space. The biggest problem is they bead up. They turn into little balls because there's no gravity or any other atmosphere that it can adhere to.
Astronauts have demonstrated the same thing when they drink liquids in microgravity. Instead of flowing evenly, the liquids separate into a series of spheres. But there is one system that would work well for keeping away the bad guys in space: launching bullets with a railgun. Railguns use a series of strong magnetic fields rather than gunpowder to propel bullets. Current railgun projectiles can already race down range about 3 times faster than a bullet from an M16 rifle.
The idea of a railgun is you take a small pellet that's maybe metal, it may be plastic, maybe whatever, but you have to have have it wrapped in aluminum foil, because you complete an electric circuit between two long rails, and the magnetic field created accelerates that little pellet out the end of the rails, and it can accelerate it very fast, up to some people believe close to the speed of light.
Similar systems are at work in certain bullet trains and roller coasters.
We have a series of magnets, and the magnets propel an object, either a roller coaster car or this giant slug of a bullet you want to use to hit something in space, from one to the other, accelerating as it goes, and by the time it's reached a certain number of accelerators, a certain number of pairs of magnets, it's really going as fast as you need it to go.
Mounted on a large spacecraft, the railgun could become the naval cannon of the future. Long rows of powerful magnets could propel big projectiles to millions of miles an hour. But would that kind of gun be enough to take out an alien civilization before it could destroy Earth? A 100 years from now, spaceships at war may blast away with ultra-high-speed railguns that destroy targets without explosives. Just by slamming into the enemy at many thousands or even millions of miles an hour, they'll release incredible amounts of kinetic energy, the energy of motion. In 2008, the US Navy tested the most powerful railgun that now exists. Using a series of magnets and strong electrical currents, it launched a 7-pound projectile at over 5,000 miles an hour. The gun's estimated range, when fully operational, will be 200 miles.
A slug, moving at 7 times the speed of sound, does a lot of damage. It's one of those things where you're glad it's on our side.
It's the kind of weapon that could really do some damage to the capital city of a violent alien civilization.
You can envision the big mothership having a railgun that runs along the periphery from one end to the other, and it could shoot a very large projectile like the size of a car or a bulldozer that you could then accelerate on that railgun maybe 10%, 20% the speed of light. And that much kinetic energy could likely destroy the whole city. I mean, that's a lot of energy.
But such an advanced railgun is obviously a long way off. So are there any kinetic energy weapons that could come to space in the near future? Remember the telephone pole-sized rod pummeling the underground bunker in our moon battle set 100 years from now? Well, that weapon, known as a rod from God, is simple enough that it could show up if a war comes to space in the next few decades. A small rocket boost would get the aerodynamic rod started.
It's basically just a big metal rod, and it'd probably be something like tungsten or some really strong and heavy metal that you can put in orbit and drop it onto the wherever you want, whatever the target is, from space, and just let gravity accelerate the thing.
Gravity's ability to speed up an object and increase its destructive power can be seen in a weapon from centuries past. The trebuchet, which is a type of catapult, used to rain down destruction from on high.
Gravity acts upon an object like this rock at a rate of 10 meters per second squared, roughly 30 feet per second squared. So if we take it and drop it, it's fallen for less than a second, has not come close to reaching 30 feet per second. But take that same rock, launch it with the trebuchet, higher, further, it will have a chance to accelerate to 30 feet per second, 60 feet in the second, 90 feet in the third second. When it hits, it'll leave a much bigger crater. This rock traveled through the air for about 5 seconds, which means that by the time it hit, it was traveling close to or around 150 feet per second. And with that added kinetic energy, it left a much bigger crater.
In the battle 100 years from now, the rod launched at the moon has an advantage over the rock from the trebuchet on Earth. Since the moon doesn't have any atmosphere, the rod keeps accelerating until it impacts the underground command post of the Separatist colony. It burrows into the moon rock and destroys the command post. But what if the Separatists on the moon return the favor and launch a rod from a space platform at Earth? Earth's atmosphere will slow the rod, but will it be enough to prevent a knockout blow to an underground headquarters on Earth?
When it hits the upper atmosphere, it's doing about Mach 25 times the speed of sound. It slows down as it comes down through the atmosphere, but if it were to hit the Earth, it would bore way down in there because it's going to hit at like 5,000, 7,000 miles per hour. So the amount of energy that's dumped in a very small space in a very short amount of time is equivalent to a small nuclear weapon.
Something like this would have a lot of penetrating power and would be the ultimate bunker buster.
But as impressive as the speeds of rods from God and railgun projectiles are, nothing can compete with the laser's speed, the 186,000 miles per second speed of light. Lasers have always been the favorite weapon of science fiction space battles.
The idea of having a personal laser is just fascinating and attractive. I would have loved one at the age of 12 myself. It's the same way that kids sometimes want to be cowboys and gunslingers. There's something very fun about the idea of having a weapon that is quick, painless, instantaneous, and makes you the toughest SOB in the valley.
But what exactly is a laser?
Lasers can be thought of as sort of a high-tech flashlight. But all the waves are in phase, so you've got all the wave crests lining up. So that makes the radiation really intense for a given amount of power. See, normal light from a flashlight or from the sun is all out of phase. It's incoherent. Some wave crests are like this, the wave troughs of other waves are like that. They tend to largely cancel out. And what you see is the leftover parts that didn't cancel out.
Most visible light laser beams appear as a certain color, since only the light in that specific color frequency is lined up and coming out of the chamber. And different types of lasers can damage targets in different ways. This green light laser at Stanford University's High Power Laser Lab pulses on and off in powerful bursts.
Is actually not delivering a lot of heat. What it is, though, is a very strong electric field. And this one can provide a strong enough electric field. By creating a high electric field, you can rip apart atoms, you can rip electrons off of atoms if you wish, and you can break down materials.
The strong electrical field even rips apart air molecules. They come back together between each pulse.
And that's when you get this flash, that's when the energy comes out, and you see the light, and you get the report that way, much like thunder and lightning.
And these strong fields are especially good at knocking out electronic equipment. In fact, the laser beam is so powerful, it actually damaged our camera as we recorded these images, when dust particles deflected part of the pulse into the lens. It left a permanent green imprint on the camera's light-gathering CCD imager. Another laser at the lab demonstrates the power of continuous waves instead of pulses. It's an infrared beam, so it's not visible to the human eye, but its effects certainly are.
It's very similar to the one that military is developing, only the military is about 50,000 times stronger. Right here we have a lens, and so as we go through the lens, the beam is focusing down in this plane here. If I put a target in that plane, you can see that we end up burning it because of the heat. And I can then take out a nice smoothly edged piece of cardboard from this cardstock.
The laser weapons of future space wars would likely work in the same way. But sci-fi movie fans may be very surprised to find out how real laser weapons will actually work in space.
In science fiction, we often see a laser bolt, a bolt of energy, whereas in reality, with a laser, you would see a beam connect and disconnect. I mean, light is the fastest thing we know of.
If you were to see someone about to shoot you with a laser beam, you would have to react very quickly when you see their finger beginning to twitch toward the button. Otherwise, you'll get zapped at the same time that you see the zapper initiate the zapping.
But in a duel in the vacuum of space, even the beams of laser weapons using visible light won't be seen.
So the reason that we can see this beam here is that it's scattering off of the dust particles in the air. In space, there are no dust particles, it's a vacuum, so you wouldn't see the beam except for at its target and reflections off of its target.
And since sound can't travel through a vacuum, none of those cool sci-fi laser sound effects will be part of a real laser battle in space. But even though laser weapons in space won't look and sound like they do in the movies, they'll still be fast and deadly on the battlefield. So what will a real space dogfight look like? You'll have to see it to believe it. No weapon has fascinated generations of science fiction fans more than high-energy lasers. And it's possible that as soon as the next few decades, lasers will be powerful enough to knock out satellites in near-Earth orbit in the blink of an eye. No weapon is faster than a laser's beam of light, traveling at 186,000 miles per second.
If we could build a weapon that had the capabilities to punch through armor plating, then you really are onto something, because if it is just electrical power that you need to drive the thing, you have what we call an infinite magazine. If you're talking about the big gun on a battleship, you have to have bullets and gunpowder. You can run out of those. If you simply use electrical power to create a laser system, we don't have to worry about somebody bringing us more bullets and where to store those bullets.
Laser weapons for use on Earth may begin showing up on battlefields any day. In 2008 and 2009, the United States Air Force conducted limited tests with a weapon known as the Airborne Laser System. It's a high-energy laser fired from the nose of a modified Boeing 747 that identifies and tracks targets so it can blast them with a precise beam of energy.
It can put an awful lot of laser energy out. The airplane flies at high altitude, and it can shoot up and take out missiles, so it's a counter-missile system. So the day is coming as technology allows us to package lasers in smaller and smaller systems. We can put them on satellites and theoretically take out missiles coming up out of the atmosphere.
And with their speed of light striking ability, lasers would be a great weapon for spaceship fighters. But futuristic dogfights between spacecraft will have little in common with today's aerial battles or what you've seen in science fiction movies. 200 years in the future, a supply ship and her escort fighters on their way to colonies on Mars are intercepted by space pirates looking for a quick payday.
Today, in an atmosphere, planes need to generate lift, which is why they have wings. Because they have wings and because you also want to keep your pilots conscious, you have long banking turns. In space, you don't need to do that. You might have a spacecraft flying along and simply turn around and shoot the guy behind him. Those are the kind of things you can do when you don't require an atmosphere.
As the pirates attack the supply convoy, the odd-looking fighters on both sides face off.
Probably the best would be a cube, covered with thrusters or little rockets and sensors. Doesn't have an atmosphere to worry about, so drag is not an issue. But you want to be able to see 360 degrees, three-dimensionally, and be able to fire in all of those directions. It would be a cube.
With these strange-looking craft fighting in the vacuum of space, the movements of the fight will also look much different than an aerial battle over Earth.
We're going to have much more jerky motion where we're allowed to suddenly just shoot off to the left, suddenly shoot off to the right while keeping our forward motion. We can throw rockets on to randomly break without having to worry about crashing down to a planet like you have to worry about within an atmosphere.
But without any atmosphere to slow spacecraft down, could space dogfights reach such high speeds that the human pilots would begin to fall apart? That's what Nicholas B. from Ziegler, Illinois wanted to ask the universe. So he texted, "At what speed do human atoms start to break down?"
Nicholas, your question actually is about a common but very understandable misconception. It turns out that atoms are stable at any speed because in their own frame of reference, they're at rest. However, humans die if they're subject to sustained accelerations greater than about 10 g. So I would say that's the practical limit for accelerations during interstellar travel, 10 g.
But how can there be g-forces in the emptiness of space where there's barely any gravity at all? It's all because of Albert Einstein's equivalence principle, a key part of his theory of general relativity. It states that gravity and acceleration are equivalent, like an elevator accelerating up, making a passenger feel like there's additional gravity pushing them into the floor.
So if you moved around too quickly in space and you jerked real quick, your brain would move around inside your skull so quickly that you could kill yourself. And so you might want the guidance system of your spacecraft to keep you from making those types of maneuvers.
Or future strategists may decide to keep pilots out of the fight entirely. So then what would a pilotless battle in space look like? Because of the complexities and dangers of dogfighting in space, pilots may be left out of future space battles altogether. Imagine our pirate ship 200 years in the future trying to take over the supply ship while all of the people remained on the two main spacecraft.
Assuming you had a large manned or piloted spacecraft that was engaged in combat operations with another vehicle the same size, you wouldn't launch fighters at it. You would throw some tiny space mine maneuverable vehicle the size of a suitcase that would be stealthy, would float up to the enemy spacecraft, attach itself, and blow up. That would be the way you do it.
But even though piloted space fighters may not be a dominant weapon in the future, lasers are still likely to play a role if war comes to space, although they will have some challenges to overcome. 30 years from now, a ground station on Earth is trying to destroy an enemy satellite with a laser. But before it reaches its target, the beam will have to deal with Earth's atmosphere.
If you've ever stuck a straw into a glass of water and looked at it from the side, you might have noticed that the straw appears to bend as it goes through the surface. This is because light gets bent as it goes through one material and into another. Well, lasers passing through our atmosphere have to deal with the same sort of problem, refraction. So when we're trying to point lasers from the surface of the Earth out into space, we have to take into consideration how much the atmosphere bends light.
A laser weapon already in space will be much more effective at taking out satellites or spacecraft.
Up in space, there would be no atmosphere, and so there'd be no attenuation of the laser light as there is when it's going through the atmosphere.
But until scientists come up with a strong, lightweight energy source for use in space, lasers won't be powerful enough to blast anything. And the same kind of energy limitations will likely keep laser weapons out of the hands of space soldiers.
Until we create a fusion reactor in a cell phone-sized battery, we're not going to be carrying those things around anytime soon that do real damage. Like Captain Kirk's handheld phaser that he shoots and destroys and completely disintegrates somebody. That takes a lot of power. I'd like to know what power source those things have in them.
So if lasers don't turn out to be the dominant space weapon of the future, then what might a battle on the surface of the moon look like 100 years from now?
As colonies often do, they get into a dispute and have some kind of war. You would think it would be fairly short. The environment is so hostile to begin with, you're lucky to be alive.
The attacking force approaching the rival colony will probably be fairly small due to the harsh conditions and the huge cost of bringing people and equipment into space. And for the same cost-saving reason, the colony will also be made from lightweight, thin materials.
It costs way too much to send stainless steel or whatever would be heavy, armored plating. That's not what the first colonies are going to be, and they're going to be very fragile.
So even a simple attack could be very effective.
I think you would just find somebody trucking a bomb over to the wrong place and sneaking it in and setting it off. Or launching a small missile at somebody. It would be incredibly hard to stop. It would be incredibly easy to get everybody killed.
But if the strike force isn't able to take out the colony right away, they might face a counterattack out on the surface of the moon. Here in the vacuum of space, even the smallest wound can be a death sentence.
If a hole were punched in a spacesuit, it would leak. And by the way, what punched the hole in the spacesuit probably kept on punching through to the person inside it, right? So how do you help that person? How do you perform first aid on them?
But the space wars of the distant future may move beyond the technology of man and machine altogether. After all, the destructive power of natural phenomena in the universe goes far beyond any weapon people have ever made. Looking hundreds of years into the future, a belligerent alien civilization is using Mars as a staging area for their coming invasion of Earth.
One might imagine redirecting an asteroid or a rock flying through the solar system so that it hits Mars. We could imagine firing a rocket to an asteroid, deflecting it ever so slightly in its trajectory so that after a number of orbits, it would finally hit Mars.
But is it inevitable that man will turn the final frontier into a battleground? Or could our advances in destructive technology be matched by advances in wisdom and self-preservation?
Human beings always think that one day soon we're going to move beyond the need for conflict. We haven't done it here, and I don't think we're going to move beyond it in space.
Most countries of the world have already signed what's commonly known as the 1967 Outer Space Treaty, preserving space, the moon, and other planets for peaceful purposes. But as space travel in the future becomes more routine, and if valuable untapped resources are discovered beyond Earth,